Hello, my name is Jiming. I'm a technical support engineer in Diana. So today I'm gonna introduce you the tutorial called Shrinkage Effect of a Concrete Slab on Ground. So in this tutorial, we will simulate the shrinkage effect of a concrete slab by using a material model called Eurocode EN 1992, which is available in Diana for the mechanical properties and also the shrinkage and the creep effect in time. So in this model, we will discuss this a few aspects. The first thing is to create a model, which is the geometry of the slab, and then we will assign the material for the concrete slab, and then we will assign the boundary conditions for this simulation, and we mesh the concrete slab. And then in this case, the emphasis is to simulate the shrinkage effect in Diana. So there are multiple approach. So here is the three of the approach. The first approach is to make use of the Eurocode material properties in Diana, which already include the mechanical properties and also the shrinkage and creep effect in time. So in this analysis, we will apply a time step, and then based on the time evolution, then we can see the shrinkage effect on the strain and also the stress of the concrete slab, as well as the crack width, the damage of your concrete slab. And in the second case, we will showcase how to use random fill. For example, in the Diana, there is a material model called Joint Committee on Structural Safety Probabilistic Model, which can be used to create a random fill on the mechanical properties on for example here, the concrete slab. And then we will apply strain load on the concrete slab to simulate the shrinkage effect on this random fill concrete. And the last analysis is another approach to simulate shrinkage, which we use linear analysis by activating the thermal effect of the concrete and adding a thermal expansion coefficient, and then you apply an equilibrium temperature variation on the concrete to simulate the corresponding or the mimic the shrinkage strain on the concrete slab. So after that, we will show you the result for the first case, the nonlinear shrinkage developed over times, and then also the second case where we will showcase how the mechanical properties of the concrete looks like after you apply this random fill, and also the strain load, and also the crack with the development based on the strain load. And the last case, we will also show you that with the incremental temperature load, we can also see that the strain and the stress developed within the concrete slab to mimic the shrinkage effect. Without further ado, let's go to the demo. So in the beginning, we need to create the project. Here we call it Slab on Ground, and then we make use of the default setting, which is the structural analysis, and also the dimension, which is 3D, and also 1 kilometer size, to make sure that the model is within the domain. And then in this case, we would like to use the quadratic mesh order, and also we will use the linear interpretation for the mid node. So after the project is created, first thing we to do is to change the unit. So in this case, we will keep the rest unchanged while we change the temperature to a Celsius degree, and we change the angle to a degree instead of radius. And the first thing is to create a slab. So how we do that? First, we create a sheet, which is the section of the slab, and we do it by adding coordinate for the 4 points, and then we create the section of this slab. And then we will also need to create a reinforcement grid. So to do it easily, we can copy paste this slab section twice, and then rename one of this to grid bot, and another one is grid top. And we will also need to make use of the move function to move them into corresponding position. So for the bot grid, we need to move upward 0.19, And for the top grid, we will need to move to 0.025. This is bot one. Yeah, and then we will need to make use of the extrude function for the slab section and extrude it in Z direction 0.22 meter. And then this is thickness of the slab. And then now we have the solid model for our slab. And basically the geometry is already ready. And next thing to do is to assign the boundary condition, which is first the support. And we first add the base support and select the face of the bottom, and then we will need to fix the translation in XYZ direction. We click create, and then we will assign the material properties. And yeah, we assign the material properties where we select slab, and then we create a material called concrete for the structure solid. And then we will make use of the Euro code. It's already available in Diana. And we select the creep and shrinkage option, and we click OK. Then you can see that all the material properties are already prefilled. Here we will need to select the class according to the tutorial, and then we will need to change, for example, the compressed behavior, and we'll need to fill in this property. In this case, I will follow the tutorial, fill in this material property. And also we will need to input the creep and shrinkage parameters. So I will change the material here to different values according to the tutorial, and we then also change the time as well. And click close and apply. Then we have the material for the concrete ready. And we will also need to assign the reinforcement property as well. And here we will add the new reinforcement material, and the class will be reinforcement, and the material model we use for Mrs. Plasticity, and then we click OK. In this case, we will need to fill in the linear elasticity, and yeah, and also the plasticity parameters. And after that, we also need to create a new geometry for the reinforcement, and we name it reinforcement as well. We will need to fill in the grid distance in both local x and y direction. We also need to fill in the diameters and spacing. After that, we click update, and now we have the bottom grid ready, and we do the same with the top. In this case, we will make use of the same material and the same geometry for the top grid as well. We'll click update, and then we will assign boundary conditions. In this case, we will need to assign a ground interface, and then we select the bottom boundary interface, and we select the bottom part, which we already assigned the support for. So in Diana, you need to assign the support first, and then you assign the connection boundary interface for that face. So we need to create a new material here. We call the ground interface, and we need to input linear material properties as well. And here we'll follow the tutorial, and we also need to input the nonlinear elastic friction parameters. Here we will need to define the cohesion and also the friction angle for this interface. We will also need to select the base support, which we created earlier, and then we have the mechanical boundary condition ready. And the next thing we need to assign the gravity, and click create is a global load, and now you can see the gravity is there. But because we are running a time analysis, we need to add a time dependent factor there. So it's basically from the beginning of the simulation till the end, we applying a factor of 1 at both time, and then we are done with the boundary condition setting. And the next thing is to apply the meshing. So in this case, for simplicity, we will assign the element size for the slab together as 1 meter, and we also need to divide all the surrounding edges using a division of 3, so that the thickness is consists of the 3 elements. Click apply, and then we can mesh it. Yeah, after the meshing, you can see the mesh is already created, and in the thickness direction, if you hide the reinforcement, you can see there's 3 elements in the thickness direction. And after meshing, the next thing to do is to assign analysis. So we add a new analysis called Shrinkage, and we add command, which is structural nonlinear analysis. In this case, we will need to remove this block because it's a low step. We will need to add the time step. In the time step, we will enter we will rename it to shrinkage, and then we will also need to fill in the time step as well. So in this case, I will just copy the time step in the tutorial and paste it there. And then we will also need to change the equilibrium iteration to 20 because it will take some iteration to converge. And we can also change it to continue instead of new starting new, just to see how the result looks like. As for the output, we will select the displacement and also the strain, the global strain, and also the principal strain. And also the stress, the global stress, and also the principal stress. And then we will run this analysis. To save time, we will skip the running process. We will just show you the result. And first, we will show you the element result, which is the total stress in S1, which is the principal stress, the maximum principal stress. And to make the result prominent, you can change the result contour plot and then adjust the color scale limit with a specific value to fill in the minimum value and also the maximum value. And then you can see that the total stress is changing with time. It's increasing with time. And if you jump to time step 27, you can find that the stress in the middle is already highly developed. And if you select the elements in the center and right click the total strain and show table, then you can see that the strain is increased with time for that specific element. You can also show both results in the same time, for example strain and stress. Here if you click S1 you can show the stress. If you click them both you can show them in the same time. So if you are interested in only one node number, you can also input this node number into the bottom left panel. For example, here we will enter the node number 2815. Then you can see for this specific node, the strain and stress is developing through the time stepping. The next will be the second analysis. So the second analysis is to make use of the random fill material. So first we need to change the slab material. We choose the shape properties again, we select the slab, and then we add a new material called the concrete C2025 random fill. And for the material model here, we'll need to select the JCSS probabilistic model and activate the random fill option. And we will start with the concrete grade C15, and then we will input the density. And then we also need to change the random fill definition. So in Diana, there's also many options to define this random fill parameters. So in this case, we just need to reduce the correlation length. Click close, apply, and then now the concrete slab is replaced with a random fill material. And then this time we will apply a strain load instead of a time load to simulate the shrinkage. We add a new set to strain load, and we select prescribed strain. We select a slab, and then we need to input the strain for the load. Great. And then we will need to mesh again so that we can create the load to assign it in the analysis. And so in the analysis tab, we need to create a new analysis. Here we rename it random fill. And we need to add a structural nonlinear analysis. So first we need to remove this and add the start step to initiate the gravity. We rename it the self-weight, and start step we need to apply additional load as self-weight to initiate the stress, and then we add a load step for this analysis, which we will apply the strain load, rename it, and then we in the load step we will select the strain load, and it will be 0.18 times. Close. And also to change the equilibrium from second iteration and then 20 times. We will choose to use the energy convergence norm, and if in case of no convergence we continue just to see the result. And then we need to add the output item. So in this case we will add again the displacement, the strain, total strain, the global and also principal, as well as the concrete the crack width. In this case we will also simulate it, global direction and also principal direction. In this case, for element result you can also show the integration point for a more accurate result, but here we just select the node for demonstration. And then we also need to add the stress, total, global and principal. And we will also want to see the mechanical properties after for this random fill, so we can choose model parameters, Young's modulus, tensile strength, and also compressor strength, close. And then we run the analysis. Then we show you the result again for the analysis too. And first we will show you the random fill. The random fill altered the material properties, and you can see the spatial distribution of the Young's modulus and also others. And in this case, because we changed the plotting values again, we need to change it back to the auto scale. And you can see the Young's modulus, tensile strengths, they are spatially varied. And then if you change the, for example, see the strain load, you can also see the crack width development. In this case, it will initiate in the center and then slowly propagate it outward. So in the analysis 3, we will introduce you about the incremental temperature load, the equivalent temperature load, which is used to mimic the strain load. So to do that, first we will need to create a new material. So if you open this concrete material, you can see that there is a thermal expansion coefficient pre-filled already. And in this case, we will need to create a new material. Use the shape property again. We add the new material. We call it the concrete thermal. And the class will be concrete and masonry and linear elastic for simplicity, but we need to activate the thermal effect. And fill in the Young's modulus, Poisson ratio, and mass density. and take into account of the temperature load, you also need to fill in the thermal expansion coefficient. And we apply, then we change the material for the concrete, and we will also need to change the reinforcement by adding a thermal expansion coefficient to it as well. And you can also change the temperature yield stress, but here we keep the plasticity model unchanged. Yeah, for we also need to activate the thermal effect for the ground interface to keep the element input consistent between the interface element and also the solid elements. And then we will need to create the temperature load, which is used to mimic the strain load using the thermal effect of the concrete. We'll add a new load case, and the load type will be the incremental temperature load. The load shape is the slab minus 50 degree of temperature increment, and then we create, and we need to mesh again to transfer the load to the element. And then we make a new analysis. So in this case, we will rename it to temperature. And we need to add the linear static analysis. And we use the default. And yeah, we do not need to change anything here, just run it. And in the result, you can see the result from different cases. So here first show the temperature. In the element result, you can see for example, the stress development based on the minus 50 degree of the temperature load. You can see the x direction of stress is equivalent to the strain load that we applied before. And yeah, in this case, we showcase you that with the incremental temperature load and thermal effect of the material, you can use it to conduct a linear analysis to mimic the nonlinear analysis of the shrinkage effect, which is very useful if you want to conduct a lot of analysis in the short time. And yeah, so that will be all for this tutorial. You can find a tutorial in the tutorial section in the website, and you can make use of the search function as well. And you can also find the relative information, which is very useful in the Diana manual. So thank you so much for your attention. We'll see you next time.